Bem-vindos to one more episode of the Type Theory for All podcast. As always, this is your host, Pedro, and in this episode, I visited in person one of the main Rocq developers in Nantes, France, Pierre-Marie Pédrot. In some ways, this episode can be seen as a continuation of the previous one, where Mario was discussing why it would be okay for Lean to break some of the key type theory properties. So I decided to invite someone who is quite vocal and knowledgeable to talk about what even is type theory to begin with, why there are some fundamental properties we should care about, both in the implementation side and the theoretical side. I'm not gonna lie, this is one of my favorite episodes so far, and I wish it would have been, episode number 1, number 0, because it is foundational to everything we do. I think Pierre-Marie did an incredible, amazing job to go to the essence, to the roots of what we want to do in type theory. But before that, here's a quick message for you. Here at Type Theory for All, we have a mission with open access and open education. We abhor the possibility of getting our content locked behind some kind of paywall. So in order to help us to deliver to you the best of type theory, programming languages, and formal methods for free, we humbly request your support through Ko-Fi. Simply go to our website, typetheoryforall.com, and follow the prompts. A donation of any amount, even $5, will be of a great assistance to our cause. Also, don't forget to follow us on Twitter at TT4All and joining our Discord. We're currently organizing a weekly study group to learn Rocq through software foundations. So if you think that's something you'd be interested in, go to the website and join Discord today. And today, again, this is the second episode that I have the opportunity to do in person. I'm extremely, extremely excited for this conversation today because I feel like I have climbed the Olympus of type theory and I arrived in Nantes. I completely butchered that one. Nantes. I arrived in Nantes, a French city where the core developers of Rocq, or the Rocq team called Galinette, lives. And I got the chance to be here with this very particular specimen of that team. Pierre-Marie Pédrot, welcome to the show. Thanks for being here.
Thank you for the invitation.
Actually, thanks for having me, right? Like, it's me who are here, not you.
Well, yeah. Depends on your point of view, but indeed.
So where should we start this? I usually like to start with talking about the background. How did you get into type theory? What's your story?
Okay, so indeed, it's a story that starts with me being French, and the fact that in France, for some weird historical reason, anything vaguely related to logic has to go through computer science. And so I started doing mathematics as a undergrad student, and then I diverted into computer science because I was a huge fan of programming languages like OCaml already by the time and stuff like that. And then I found that it was much more satisfying to do programming language theory than mathematics. But still, this mathematical background of mine, like the fact that in France you find all the logician people there's a strong tie between PLT on one hand and logic, the study of logic, is really a very French thing you can find in all the computer science departments. So I went into a rabbit hole of trying to make my type systems as precise as possible, and then I ended up here doing type theory, for the good or the worse, I don't know. So basically I've got this kind of bicephal take on I like to see things in terms of mathematical objects because I'm still somehow, to some extent, a mathematician, although most mathematicians would disagree. And I'm also a computer scientist, even though most computer scientists also disagree. So here am I.
So you're saying that you're developing some, you wanted to do the type system of your language. What kind of languages were working?
But I was not designing the type system per se. Rather, I was studying, I had maybe one of the most striking moments in my pre-logical life was the discovery of a continuation passing style. And the fact that you can actually realize classical logic through it was oh, this is mind-blowing. And the fact that, so there is that thing that logicians have been studying from the 30s, like a Glivenko theorem is very old. And there is that thing that has been used by programmers in the 70s, 60s to write compilers. And these two things are actually the same thing when you write them together. Just say, And yeah, so I'm really a Curry Howard baby, I would say. This is like an eye-opening moment. Like, oh, whoa, that's so nice. I should do that. So I've been indeed studying since then, trying to make things like extend the Curry Howard in terms of expressivity. Like type theory is really a very nice realm to talk, because it really makes the Curry Howard isomorphism. There is no not any difference between logic and computation in type theory. It's like it's the same thing. There is no way to make a difference. It's just a point of view, and this is really a very nice setting for this kind of study.
I think you already touched on a lot of topics that I want to go a little deeper into each one of them, and I have a little bit of trouble to choose which one to begin with. But you're talking about the Curry Howard isomorphism, about continuation passing style, about realizability, and this is all in the heart of what we do in type theory. So, but before we get too technical, and I really want that, let's. I'm still curious. What personally speaking, what was your path to end up being a Rocq developer? How did you get here?
Okay. So it's a typical. Okay, my path is not special in any way. So how in the history of in the prehistorical times of Rocq development, how did people end up writing Rocq? It's typical. You just start a PhD in the laboratory where Rocq is developed, and then slowly but surely you get attracted into the development by all possible side channels. So I started actually writing my real entry point into the Rocq development was writing Rocq ID code, actually.
Oh, really?
Yes.
Wow.
Because I was fed up with the so I was already a Rocq user by then, and I was fed up with the interface. So at the time we didn't have a lot of choice. Either you had the proof general approach, and I'm really allergic to Emacs. so no way I would use Emacs, so I chose the other one, which was Rocq ID. And at the time, Rocq ID is still very crappy, but at the time it was even worse than that. So yeah.
No, I would argue that compared to when I started in 2014, 15, oh no, Rocq ID today is another beast entirely. It's so much better.
Yeah,
so much better.
It is indeed true. It's not all due to me, but I did contribute a little bit to the enhancement of the thing. And then one thing leading to another one, I ended up cleaning up horrible code, because when you start reading the code, so really I think something that people might not be completely aware of is that there has been a huge change in the Rocq community at large, ecosystem, I would say. It used to be an extremely reclusive development, like people would, the only way to get your code was basically to know somebody in the Rocq development team, and it was like real prehistory, like dinosaurs. We were using SVN at the time, so writing branches was out of the question. So that was really a horrible. Releases were tied to the release cycle was tied to weird political decisions about what's going to be merged depending on the PhD. Because typically the thing you would do then, you would a PhD would come, study something, implement it in Rocq, and then that would be released at some point. So there are a lot of that was how the kernel was developed at that point. So if you were not a PhD student in one of these teams, then basically there was no way to get your code in, and therefore it was really a different world. Nowadays it's much more open. If you were on GitHub, the code is really open. You can submit pull requests. So if you're trying to touch the kernel, maybe we'll be a little bit more careful than everything else, but we'll consider your pull request. But at the time, it was basically impossible. So yeah, so I was reading the code of the. So I'm still an OCaml programmer. I was reading the code at the time, and I thought, holy cow. How is it even possible to have this kind of hodgepodge of horrible mess of styles and very bad designs of it was really horrible code. Some of the stuff there are still remnants of it today, but we're slowly cleaning the code. So yes, one thing leading to another, I ended up modifying huge pieces of code for cleaning up, and then I ended up modifying the kernel and a lot of other things, and then I got into LTAC development. I think at some point I'm still scarred.
Oh, so it's you who we should blame for LTACs.
No. Please. Okay, let's give back things to Caesar. I did not write LTAC. It's very hard. Okay, so if I can make a little parenthesis on LTAC. It's an extremely funny piece of code. So we have a few similar components in Rocq, which is the code that, like, I would call it maybe like Heisen code. Like, this is a kind of code that if you stare at it for too long, it will break a development somewhere in the wild.
Yeah.
So yeah, proceed with caution. And yeah, so I did clean up a little bit of LTech implementations, which led me to the implementation of LTech 2 when I realized that there was no hope. And yes, basically.
Nice. Okay, let's start getting technical then. I think the right question to begin with is, how do you describe what is type theory?
That's an extremely good question. So it really depends. I'll take my Kerry Howard hat, and I have like several, like quite a few different answers depending to whom I'm talking to or what's your background. So I can start with the one I came from, which is maybe the most natural one for say computer science. So if you study type theory in this light, basically it's just like a super nice programming language. And a programming language that has like this extremely powerful type system. Somehow you can climb the stairs of expressivity, starting from like simple type lambda calculus, and then you go to system F because you want to be able to parameterize your types, and then you realize that you would be happy if you had like this kind of like computation in type. So then you get to F omega, and then you realize that actually maybe I should be able to actually have types that depend on terms, and then you introduce dependent types, and then you get to the calculus of constructions, and then you realize that it's crappy because you do not have enough expressivity to actually compute properly your types. So you throw in the mix inductive types with large elimination, and ta-da, you get up with the Martin-Löf Type Theory. So this is like this is a programming language built from the ground up. That is very funny because, like, if you compare it to other programming languages, like most of if you take the vanilla programming language from the real world, is designed with like actual machines in mind, right? So you've got these like low-level interfaces, like, you know, how to like the compilation phase is very important. So you need to reflect properly in your language the minutiae of your actual machine you're running the thing on. And this is not the case at all if you look at like Martin-Löf Type Theory or type theory at large. Like, most of the things you could find in your run-of-the-mill programming language is not there. Like, you have no side effects. You have all functions terminate. So the usual joke I make is like okay, you want to teach Rocq to a fellow programmer, and you say, oh, that's a super programming language. Like, can you write a hello world, please? And you're like, no. So it's a bit weird from this point of view, but clearly it makes the programmer happy to be able to reason natively in the programming language and in the logic, like the fact that you can actually ensure that your programs are bug-free is really a marvel of this result. But that's only one way to arrive to the Martin-Löf Type Theory in general. The other one, so I mean, there are several other ones. Another one you can start from is like somehow parallel through the Kerr-Howard correspondence through logic. So you say, oh yeah, so okay, so I want to do mathematics, so I need some foundation to do my mathematics. So typically you start by saying, like, people at the beginning of the 20s, they were very careful about, yes, I'm going to use the simplest possible system. So yes, you've got these like combinators with basic arrows, right? So you say, I don't know how to do and or not implication for all first order. Then you realize that it's a bit annoying. So you actually want to get into more expressive systems. So you follow the same, you climb the same ladder as before by adding more higher order logic and whatnot. So basically they are in one correspondence through the Kerr-Howard correspondence, but you can arrive precisely at the same results by just taking a logical approach. And there are more ways. So I'm less, I wouldn't say familiar, I'm less fond of the other approaches. So some people claim they can arrive to Martin-Löf Type Theory through category theory. Okay, I will withhold my judgment on category theory for now. But it is kind of true that some of the things you could, like, maybe not exactly category theory, but you can easily get into type theory by doing universal algebra. So, this is the kind of stuff where you say, oh, I've got these term and type formulas, I've got such and such equation, and then the way you write them very naturally is like a derivation sequence, like a sequence as in type theory. So it's a very natural thing to also arrive at type theory through universal algebra. So it seems that more generally, so I'm not an expert in these areas, but it also seems that type theory is so ubiquitous and universal that you can find it everywhere. Like, it seems so that most of what mathematicians are trying to do nowadays when they are constructing these super weird systems, like there was this what was the from my maybe I'm completely wrong, but my understanding of what the mathematicians were doing with the liquid tensor experiment thing is somehow to design an internal language to reason about the complex mathematical objects. So mathematicians seems to have reached a state of complexity. I mean, it's not new, but it's getting worse by the minute, that the objects that are manipulating are so complex that you never want to interact with them with the real object. So you build up like layers of abstractions to reason about these objects, and most of the time what you end up with is basically some kind of type theory. So you're describing, so it might not be exactly Martin-Löf Type Theory, but you have like the basic type formulas like for all quantification, implication, blah, blah, blah. And then somehow this is a bit like universal algebra, but starting from another point, like a concrete point where you know what your objects are, but they are so hairy that there is no way you're going to be able to prove anything if you look into the nitty-gritty details. I like to consider it as like some kind of assembly. Like, type theory is basically all about climbing this ladder from whatever assembly you have at hand, be it like lambda calculus, what was the name of the thing? So yeah, logic, what was the name of the liquid tensor experiment thing? Like I don't remember the name of the object they were considering, but whatever. So there are you take whatever crap you have to work with, and you're trying to design a principled reasoning system atop of that, and somehow it seems that empirically you always end up with something that looks like type theory, the ultimate syntax, if I might say.
So let me see if I got something right, because this is something that always kind of like trips me a little bit when I'm reading papers or something. Every time that we're talking about type theory, you end up talking about Martin-Löf Type Theory. So what I could gather from the way that you're saying, so Martin-Löf Type Theory is basically calculus of constructions plus inductive types, which is calculus of inductive constructions plus what else?
It's already not quite true. It's less than that. It's more and less than calculus of constructions. So like, people really love debating about what is type theory, what is Martin-Löf Type Theory, what is CIC. The answer is that these objects are neither well-defined nor even uniquely defined.
When I'm reading a paper and I see Martin-Löf Type Theory, what should we have in mind?
So Martin-Löf Type Theory is like what you could expect from such a thing, is like at least one universe, maybe a hierarchy of universes, and then a few type formulas. So typically you would expect natural numbers. So, okay, pi types is always a given, and sigma types also. Mm-hmm. You would typically expect natural numbers, equality, and unit and falsity. And then if you're really fancy, you can throw in the mix W type and stuff like that. Uh-huh. But it's not a very well-defined object. You can call something a Martin-Löf Type Theory, but there is the reference Martin-Löf Type Theory from the 72 papers also. It's not what people usually call Martin-Löf Type Theory, because like there are so many variants that...
I see.
Just like when you say even simple type lambda calculus is not even that well defined. For instance, like if you look at things such as like, is your lambda calculus like Church style or Kerr style? Nobody says so, right? So it's things that are very similar and more or less the same.
Gotcha. I think it helps me to understand things a little better, for sure.
Yeah, I can insist a little bit on the differences between what people like to call COC, CIC, COC, this kind of stuff, compared to Martin-Löf Type Theory. So one major point of departure in terms of expressivity. So in terms of implementation, that's really nothing, because like it doesn't change anything. But in terms of expressivity, the major difference between this kind of French style, so that's what I call there are two schools of dependent type theory. There is what I call the Franco-Dutch and the, how would you call that, like Swedo-Scottish or Scoto-Swedish. And these are not, there are many differences, like very subtle differences. Like it's really these are two kind of dialects of type theory that are kind of at odds with one another. So the Franco-Dutch thing typically like is where the COC, CIC, and COC stems from. So they typically have an imprecative universe. So that's very expressive in terms of logic, but in terms of implementation, it doesn't change. Like it's trivial. It's really just an easy rule.
What does that actually mean?
So it means that you have there is a universe called usually prop, such that the type of product, so the pi type. So you take a pi type a pi type is something that takes a type, and b function from a to type and turns it into a type. Then with an impredicative universe, say prop, then you can also form pi types returning a prop. So now we have a b from type a to prop, and for all ab of type prop. But a can be in any universe. So basically there is some kind of like you're squeezing huge data, because like the A type, like the dominant type, can be as high as you want, but it's gonna fall into something that is small, and that's the heart of impredicativity. And the for like what I would call like maybe not psychiatric, but like almost psychiatric reason, the Scotto-Swedish school has a very strong distrust for impredicativity.
Really?
Yeah. So the original Martin-Löf paper had this famous type rule, which is very well. So there's that. Maybe you've heard that anecdote already, but Girard published a paper about the fact that this was inconsistent, right? But actually, like by the time Martin-Löf was writing the paper, he knew that it was inconsistent. He waited for Martin-Löf to actually publish the paper to say, "Hey, this is wrong." Yeah. And yeah, so they got burned from this, and with so there is some there are some like it's more in the domain of philosophy, but I mean, as a computer scientist, like impredicativity is something I eat for breakfast. So I'm really not afraid of impredicativity.
Okay. So just to be clear, so there are notions of impredicativity that is known to be inconsistent, but
I mean, it's not impredicativity. It's something that shouldn't be called impredicativity, but that people confused due to historical reasons with the other one. So that's one difference between the Franco-Dutch and Scotto-Swedish school. There are also other subtle differences, like for instance, does your equational theory stem from? So in the Franco-Dutch school, typically you would define a conversion. So the rule that says that you can replace a type by another one in the derivation, assuming they are equal. So conversion tells you when they are equal. A conversion in this school is more defined in terms of untyped reduction. So you say that two things are equal if they basically reduce to the same thing. Whereas in the other school, they would rather be like typed equational theories. So they are more on the algebraic side, saying we've got these and these rules that allow me to say that, for instance, lambda applied to an argument is going to reduce by beta rule or something. So it's not a reduction, it's an equation. Whereas in the other side, you would get something defined just by reduction. And in one case, it's easy to fall in the situation where your reduction is untyped because it's more natural. You just say, I take two terms regardless of the types. I normalize, I looked at the wicked normal form and I compare recursively. Easy, you don't need a type. But in the other direction, you typically need types for eta lows, like saying, for instance, if something has a function type, then it must be convertible to, so if m is type pi x a b, then m is actually convertible to a lambda x m of x, if x is a free variable or something. So that's another difference. And maybe a third one I could say, which is also, so it's very funny. I recommend you to read the old papers from the 80s. Like there is a lot of confusion going on there. It's like a second crisis of foundations. When you read the papers from the 20s, 30s, assuming you can read German or something, like there's a lot of like confusion all over the place about basic principles of logic that any like undergrad would take for granted nowadays. Like if you did a little bit of logic, it's obvious. Like things like this Löwenheim's column theorem is like paradox is not paradoxical at all. It's if you phrase things correctly, it's obvious. But there's the same thing going on for type theory. So the 80s was like this moment of like some kind of a bubbling up of a lot of ideas, and people were utterly confused. And for instance, one difference between the Franco-Dutch school and the Scotto-Swedish one is the use of recursives in one case and use of fixed point and pattern matching. And there are interesting papers where they say, oh yeah, so but with pattern matching you can derive the K rule, the rule that says that all proofs of equality are equal to reflexivity, which you can't do in with a recursor. But the reason it has nothing to do whatsoever with the use of pattern matching versus recursors. It's just that the rule for the pattern matching is the wrong one. So you could have the same rule, you could have the same thing for the recursor somehow. So it's really funny that you can see this kind of confusion arising in this context. So yeah.
My trouble reading those older papers is that, like something like me who's just doing the PhD now, the way they speak is so foreign nowadays. Like, so like the jargon, like the words.
Have you tried reading papers written by categoricians? Like that's even more foreign.
Exactly. But since even notation back then sometimes it's very different. I mean, I tried to read Principia Mathematica one time. Oh, that's unreadable. That's impossible to read these days.
So if I can make a little bit of advertisement for article book, I really appreciate it, which is might be of interest for the French audience. And so it's written in English, but it explains. It's a very good explanation for the current mess that is the research of logic in France, and it's called Bourbaki, or the Scorning of Logic. So it's a very nice paper about. So the long story short, the competitive examination for teachers in mathematics in France, it was written in the text, like the law. It was written that it was forbidden to do an exposition on formal logic. Right. So because you have to give a lesson, whatever, it doesn't really matter, and you have a list of topics to choose the lesson from, and it was forbidden to do logic. And the reason actually dates back to Bourbaki, the Bourbaki group being completely confused. Like this article is it's a very long article. Maybe it's 60 pages or so. I don't remember. And it has a lengthy extracts from a lot of Bourbaki groups, literally pinpointing confusion about logic. And because they have basically the French mathematicians, they have had a huge despise for logic, the Bourbaki group in particular. And since they shaped the research in mathematics in France, we ended up in a situation where basically no mathematician does logic in France nowadays. You have to be a computer scientist. So it's a kind of interesting thing. And there is a widespread confusion about the axiom of choice. And in the site, there is a book by Godemont where they cite Principia Mathematica, and it's almost shameful to some extent. It's not clear that they read the right thing or something. They're quoting part of the. Well, I really recommend reading this article. It's very interesting.
So let's go back to another point. How do you describe? So you're saying how what we're doing in computer science is really doing math, right? And this is the heart of the Curry-Howard isomorphism. Can you tell us a little more about that?
Yeah. So maybe we should start with a little bit of history, right?
Yeah.
So I don't remember the dates exactly, but Curry was the first one to realize. So it is not exactly a how would I put it? So there is this kind of stupid but brilliant ideas, right? Which are obvious when you state them, but that need to be stated to be actually worthwhile. And the Curry-Howard isomorphism in its barest existence is precisely like that. So what happened? So Curry, yes, in the what's
Clean.
I don't remember
there was
the date.
Church, Curry, Clean, Curry, Haskell. I never get it.
So Curry was probably the first one to realize that.
Yes.
It's basically you take combinatory logic, and then you take maybe I'm confused. No, I hope I hope I'm not saying. Please correct me if I'm wrong. But I think the first person to realize that was like the equivalent between combinatory logic on one hand and combinatory lambda calculus, which doesn't mean anything, but the SK reduction system, right? I think that was the first realization. So you just see that this is the same thing, and maybe the more modern one was just you take the rule of natural deduction on one hand, you take of minimal natural deduction, and you take the typing rule for the simply typed lambda calculus. And these are the same, it's the same picture meme. There is nothing to do. It's not even a theorem.
Right.
It's more than a fact. There is nothing to be said.
Yes.
But once you've said that, actually you've said a lot.
Yes.
Because it's opening a brand new world of research and interesting things. Because suddenly you have this Rosetta Stone where you can explain one phenomenon or one concept from one side as a phenomenon on the other side. So if you just look at simple type lambda calculus in natural deduction, so for instance, you can already realize that the cut elimination, for instance, because it's not only about derivations, because that would be boring. There is a very well-known concept in logic, which is called cut elimination, where you take a proof, and then there is what is called a cut, which is basically in the case of natural deduction, a call of an elimination followed by an introduction, or the other way around, depending on how you see your proof.
The idea is that, like how I see cut elimination is that your proof now is algorithmic, right? Because cut is where you have to be a little smart, right?
Yeah, a cut is like you're making some detour in the proof,
yes, right.
And actually this detour was not needed.
Yeah.
And if you look
Which is very surprising, actually.
Well, not if you look at it. That's my point. If you look at it from the point of view of lambda calculus, then there is nothing funny here, because it makes sense to write functions, because that allows you to share code and actually abstract away your implementation, because you don't want to repeat the same program I don't know how many times.
Yes.
Write it once and then you apply it several times. And then the cut elimination is precisely doing the very same thing as beta reduction. Like literally, you take your derivation, you apply the cut elimination on one node, and you look at what it means through the Carey-Howard lens in the programming language, and that's literally beta reduction. So this is wonderful, because not only we said that the derivation systems are the same, but actually there is a computational interpretation of your derivation system that was somehow hidden, because they knew about cut elimination already. But if you look at the original version of cut elimination, these are typically done for classical systems, and then cut elimination in classical systems is not very well behaved, because it's typically not confluent, so you get into critical pairs, and you can explain this phenomenon through the Carey-Howard lens, which is basically that you're confusing call by name and call by value, and then in an effectful world, call by name and call by value are not the same. So that's what you get into this confluence issue. So you can start from these very basic observations. You can really start writing your Rosetta Stone in a lot of different dimensions. Because here I mentioned, for instance, I mentioned dynamics. So this is saying I can interpret logic in terms of dynamics. That's one thing. I can interpret logical. So the thing I mentioned before, this phenomenon of badly behaved cut elimination classical logic has already an explanation in terms of programming languages. You can also express things. So we're somehow treading already on the territory of realizability, but you can explain some logical interpretations as a program translation. And that means that actually by doing your logical interpretation, you're enhancing, you're compiling your program into a different programming language. In this compilation phase might add new behaviors. So you can actually, there is this very funny equivalence between, what if I take my lambda calculus, so now I'm taking it somehow the other way around, right? So I'm taking my lambda calculus and I'm adding new computational primitives to my lambda calculus. So the most famous one is called CC, for instance. That's the one that ushered the era of classical reducibility. So called CC is like this weird primitive from Scheme that if you try to explain it, you really need to write down what it means, because it's extremely confusing. And there is nobody really knew what it meant until Griffin at the end of the 80s. He was working on Scheme and trying to type the called CC primitive, and basically realized that it had this fancy type called Peirce law, right? Which is right. A implies B implies A implies A, all parenthesized on the left. I think he mentioned that, maybe I'm inventing, so please double check what I'm saying again. But I think he mentioned at some point that he did not realize immediately what he discovered. So it was he was wandering around asking, "Have you seen that type?" Doesn't ring a bell, And somebody told him, that is Peirce law. It's a very well-known rule of logic that gives you classical logic. So suddenly people realize that, actually I can extend, by extending, that means that I have a type system for my lambda calculus plus call CC, which somehow validates classical logic. So that means that by adding new computational power to my calculus, I actually get new axioms in my corresponding logical theory. And this kind of equivalence can be really lifted to a lot of things. So for instance, I don't know, I can give you a list. There are many things. So forcing, for instance, forcing is one logical interpretation. Okay, maybe I should say, before leaving the topic of the call CC thing, call CC can be implemented through double negation translation, like a CPS. You can have if you do a CPS for lambda calculus, you can, in the target of the CPS, you can implement call CC. And the CPS precisely corresponds to double negation translation on the logical side. So really, there is a perfect, nice commutative square, I might say, between your logic and your programming interpretation, where you say, actually, this new primitive corresponds to an axiom, and I can get rid of the axiom by translation. I can get rid of the primitive through a translation. Oh, holy shit, these are the same. Yeah, and you can go like a lot of fancy logical interpretations are actually compatible with this interpretation. So, okay, I can give you a list of few if you want.
Go ahead.
Yeah, so okay, forcing, for instance, if you take intuitionistic forcing, if you look at what it does in terms of computational interpretation, basically it's adding some kind of a global cell that you can read in a World Cup way, and that is monotonous. So it's a kind of a well-behaved state, monotonous state. You can only increase the data in your state. There is the famous Friedman's trick that allows to show some kind of fancy conservation of pi02 statements over classical logic. Doesn't really matter what it means. But if you look at what the proof actually does, like it's a nice translation, logical translation. You look at what the translation does, it's just adding exceptions, right? So I have a way to escape from my context through exceptions in my language. So already it shows you something funny, which is that the resulting theory is inconsistent. Because like, with exceptions, you can always prove any type, right? Because like, you have to prove false, you say fail. Fail is a proof of false.
Right.
But since you're clever in the way you interpret your exceptions have payload. So they contain, you have to raise with something. You have to give an argument. And the funny thing is like, you can actually use that, use the fact that the type of exception has some computational content to extract data out of it, which is basically how the conservativity result is obtained. You're extracting data, even though your theory is locally inconsistent. There are many more things. So what could I say? So there are these funny things where if you have a fork, like if you have threads, you can also prove classical logic, but in a different way. So basically, you just like duplicate your state and try to see which side is correct. Yeah, there are. So this is used in classical reversibility for laugh and giggles, but it results in badly behaved models. What else? So I'm trying to find. So reader, what are forcing? Yeah, the classical part of forcing, which is we can be generalized as Schiff models.
Oh, but you said you hate category theory.
Yeah. No, I hate the language in which it's phrased. It's not because you speak, like, once again, like you can speak, we're speaking English. I hate English with a passion.
Of course.
Nonetheless, yes, I'm French. So nonetheless, even though I hate English, I'm using it for communication because I'm forced you don't speak French, so I have to use English as a common language. I'm fine with that. And furthermore, it's not because English people are using the most disgusting language ever that they are not discussing reality, right? So it's not because you can choose your favorite language to discuss reality, but reality is still out there. So both sheaves and whatnot, they can be phrased in a perfectly sane way that doesn't require category theory. Like if you ask, like I have a lot of pet peeves, but for instance, if you ask like the categorical definition of a tripos, like good luck trying to understand what it means. It's just basically trying to implement something very simple in terms of like high order logic, and it makes a lot of sense if you write it as syntax. But if you look at the categorical definition, you're like, what the hell are they trying to say? So yeah.
So I think it's a good point to also bring category theory actually to the journey too, because it's not only the Curry-Howard isomorphism anymore, right? It's the Curry-Howard-Lambach. So now all of this is also in terms of category theory too.
Yeah, they claim so. I've personally never been able to understand. To me, it looks more like, when somebody is very successful, he tries to retrieve a little bit of the remains from the feast. Mm-hmm. So it's true that category theory did bring a little bit of expression of comprehension to the mix, but I think there is a little bit of revisionism in there. Like it's more after the fact that like the timelines are not exactly the same. And in category theory, for instance, the category language is extremely weak when it comes to a lot of very important things like dynamics. Because category theory only talks. I mean, everything can be on category theory. It's just a language, or you can axiomatize what we need. But the natural way to phrase things in category theory is completely oblivious to computation. You only have equational theories. So you say here are two things equal, but never you would talk about reduction actually as a concept. And I think that if you do programming languages only in terms of things are equal, then you are not really doing programming languages. So they constitute a nice model when you care about this kind of how would I say what's the name? the name escaped me, but not definitional, like the contrary of operational models.
Denotation.
The category theory are very good when you talk about denotational models, but it's only a small part of the picture. So I would once again, I think there are a lot of good concepts that were found in category theory. So one of them being the concept of adjunction, I think is like a critical notion that should be taught way more around. But you do not need, it's not because it has been discovered in the category realm that you really need category theory to describe it. So, okay, adjunctions are very nicely described in terms of category theory. But the notion makes sense even outside of category theory, and is a very nice one. More generally, okay, my hot take again is that a lot of, that's a personal take. I know a lot of people who disagree once again, but I am deeply convinced that category theory for a lot of things related to type theory are mostly obfuscation. There are a lot of very nice concepts you can write when you use it's all a matter of syntax, because that's the difference between type theory and category theory. Now both syntax is to talk about your objects in the meta theory. So it's a way to present things. So some notions are more easily amenable to one formulation in one setting and not the other. So for instance, once again, the adjunction thing is very elegant to write in category theory, but a lot of things are completely horrible if you write them in the category style, because category theory is basically a first order language. Like there is a deep hatred from mathematicians. I don't know why. This is something that deserves, I think, psychiatric analysis or something. But there is an extremely deep hatred from the mathematicians about the high order syntaxes. That they really hate binders. Like binders bad. Like they want to write everything as first order objects. So you can see that already in the Cartesian closed category presentation. Like when you write lambda calculus, you've got these nice variables, you're happy, blah, blah, blah. But when you write the equivalent as a Cartesian closed category, which is supposed to be a complete model for simple type lambda calculus, then you get into trouble because you only have access to something that looks way more like combinators, right? You can only just say, there is no first class notion of lambda abstraction. You can say, can you have this adjunction between the tensor, the product and the arrow, and then something happens. But you do not have a first-class access to variables. They are an emerging concept and not something built in. And when you do dependent type theory, like dependency is everywhere. So you have to write variables like everywhere. So every time you write something that is even like miserably dependent. If you look at what the category theory people write, it's completely horrible to say, look at this morphism that makes such and such diagram commute. But actually, you could just write it as a simple, like linearized term, but it has variables. So you can't do that. It's completely forbidden in mathematical language. Like they don't like that. So I think that for most of my daily use of even mathematics, actually, I'm extremely biased in the kind of mathematics I study, I do type theory. I really think that most of the historical presentations of category theory are counterproductive. They are hiding a lot of simple concepts under a lot of encoding artifacts. And I can give the example. The typical example is the notion of dependent type. When you ask a category theoretician how they do dependent type. So the natural way to do that is to say, actually I'm going to do so I never remember whether it's indexed or fibered, I think, right? So the one where you say, there is no such thing as a concept of dependent time, so you have to build it from scratch yourself. So you're gonna say, that's actually like the total space. So you replace B of type A to type by like the set of there exists an X in A such that B of X plus a morphism saying from that to A saying actually the first component of my type, the morphism is telling you what is the first component of your dependent pairs. So you're basically replacing a dependent type by a subset of dependent pairs, assuming you can define dependent pairs, because you don't have first class access to dependent types. So since you don't have high order syntax, then you can do it. You have to do everything through first order presentation plus equations. And this is very inefficient in hiding a lot of easy concepts under a lot of minutiae of actually trying to reason a thing. So yes, in the realm of dependent time theory, a lot of category theory is like extremely weird.
Correct me if I'm mistaken, but when it comes down to I'm also kind of still learning, and I've been to some summer schools in my time here. And one concept that I've been trying to get a better hold of is that of, when we're talking about giving a model to lambda calculus, it seems to me that it means that we're trying to understand what lambda calculus is doing by looking into some well-behaved mathematical concept that, the mathematicians already understand very deeply, and we can use those tools to show that, this is doing something we know that works, right? It's well-behaved somehow. I've seen a bunch of papers, especially nowadays, that, gives a model to some programming language in terms of some categorical semantics, because then can show how certain things are well-behaved in that model. So
yeah, so there is, okay, might not be the best one to actually rant on this topic, but there's, in the case of PLT in particular, there is quite a bit of Congo cult going on about the precise, so I think there is either an impostor syndrome or even like some inferiority complex from the computer scientists, and they have to cling to serious sounding things. So categories fit that bill by being you were doing a categorical model is very serious because that's math. But if you really look into the details, these are actually pretty simple concepts. I mean, I would be hard pressed to define what it means to be a categorical model. Actually, it's the category. What was the adjective for categorical nature of something is in the eye of the beholder. Another pet peeve of mine is the fact that people call categories families categories. I mean, there are no. Okay, there are categories in categories families, but they are like on the margin. There's nothing. You don't need categories to explain. I mean, actually, you need non-categorical objects to define what is a category family. Like presheaves are non-categorical in some way. You're talking about sets or whatever types you live in your meta theory. So I'm very cautious of the fact that people urge like the whoever wrote the model to be a categorical model. Like some models are once again more amenable to be presented in an elegant way in category theory, but it doesn't mean much. Like everything can be categorified if you want.
Okay.
It's just going to be ugly. Or the other way around. Every horrible category. Once again, look at tripos. Tripos is, or what do we call them? It's like, okay, you get a category model. What are you asking for these things? And you write the syntax. That's what you actually meant. Okay. Yeah, so... Sorry, what was the question? Like models of lambda calculus in categorical models? Yes.
Yeah. I think we covered that pretty well. Let's go back to type theory. And so in our conversations that we've been having this couple of yesterday and today and the time that we're in Birmingham, it's one thing that stood out to my attention is that you'll see where I'm going with this. You know right where I'm trying where I'll end up going. But it seems to me that there, when we say that, okay, we're doing type theory, there are certain properties that we want our type theory to hold. Can we talk a little bit about what are these interesting properties that we want in our type theory and why we want them?
So there are quite a few, so depending on whom you ask to, so I can give a list of things I care about. Some people might disagree with the fact that they are important, but okay, something people seem to care about for some reason is consistency. So consistency is like the easiest described one. So type theory is consistent when not everything is provable. Okay, so that's an easy criterion. So if you come from logic, then you do care that your type theory, your logic system is consistent. But already as a computer scientist, I would start to disagree. Or maybe I should list the properties and then negotiate. Okay, so consistency is one of them. One property you care about, which is like finer, stronger than consistency somehow, is like a equational consistency. So typically saying that true is not equal to false, but with the notion of equality, which is conversion. So your programs, the programs true and false are not the same for a good notion of being the same, the strongest one you could take. You care about properties I would call practical. So one of those is like decidability of type checking. So that one is important for several reasons. I would like to come back on that after. You want to be able to have a computational interpretation of your type theory. So there are various ways to phrase that. Morally, most of the time we define that in terms of canonicity. So canonicity says that your programs have normal forms that are well behaved. depending on who you ask, once again, you get different answers about the way you define canonicity, because there is like a mathematical way that doesn't tell you anything about how to compute these normal forms, and a computer science way to actually say, yes, there is a normal form, but in addition to this existence, I can actually compute it. There are other properties that are less often considered in the which is like the simplicity of your type theory. Because like once again, it's like, but that one is mostly it's not an objective property of your type theory, but like the fact that the type theory needs less concepts to define the same things. What else do we care about? Did I miss something?
Consistency, equational consistency, type check indecidability, computational interpretation. Do we care about progress preservation kind of thing?
Yeah, there are. Okay, so there are part of the canonicity thing. So these are properties that are like secondary properties that are typically needed for the other properties to hold. So indeed, you care about subreproduction. The progress and preservation are basically equivalent to canonicity, depending on how you phrase it. Like, it's just that in the world of programming languages, since you usually have non-terminating programs, you have to be careful. But in type theory, we most of the time have terminating reductions, so the setting is much simpler. But yeah, all the usual properties you ask for your type system. Okay, soundness is somehow what is usually called type soundness is subsumed by, I guess, equational theory, the equational consistency. Like, it's a consequence of equational, because you can't substitute. Like, if you have, what else do we care about in programming language theory? Yeah, one thing we explicitly not care about is Turing completeness, because most are due to Gödel and completeness theorem. Okay, so I know that people are very vehement on the internet about what it means to be Turing complete. There is an interesting flame war going on the proof assistant Stack Exchange.
Stack Exchange, okay.
Yeah.
I thought you were going to say Reddit.
Probably in Reddit, but I do not lurk enough on Reddit. I mean, the ratio, noise information is not good enough. But like on the proof assistant Stack Overflow or Stack Exchange, it's good enough that I read it. And there is a thread where once again, I think we're bordering psychiatric issues, but for some reason, people take it very seriously, the fact that, MLTT is actually Turing complete for a notion of Turing complete, which is not the one usually agreed upon. So, yes, the sky is red if you define red as blue.
Right.
I mean, I'm fine with that. But like there are things that are mathematical statements, and once you agree to a specific mathematical statement, you can, assuming a strong enough meta theory, decide whether it's true or false. Oh, I'm outing myself as a Platonist once again. Assuming that, normally you should be able to tell whether it's true or not. And in the case of Turing completeness, for all reasonable definitions of Turing completeness that are actually the ones usually taken in literature, right? Then MLTT is not Turing complete, and this is due to Gödel and completeness theorem. Because I can come back to that after if we talk about decidability of type checking. So yeah, it doesn't really matter to be Turing complete in type theories. It's actually a defect of your type theory if it's the case. And somehow it doesn't really matter because like for all practical, I mean, every single program written by a human being, apart from an interpreter of MLTT, is writable in MLTT, right? So this kind of escapism in it's just like a set theorist, like they care about the size of the cardinals. There's the same thing in like this kind of expressivity of logic, saying, I'm able to prove my language is the most expressive one. In the case of programming languages, there is a bound, which is like achievable with Turing completeness. But due to technical reasons, we can't do that in type theory. So you won't have the most expressive, but not Turing complete system. And basically it doesn't really matter because in practice that's completely irrelevant to the actual things you do with your type theory. Like apart from really trying to diagonalize your interpreters, it's useless. So should I go back to each of these properties or? Okay. So starting with consistency very briefly, I can go back to that. So consistency, no, not everything is provable. Very important for logic, but for computer science, we don't care. I would be happy with an inconsistent type theory. The reason for that is that there is more information in your type theory than merely being provable. There are various ways to be provable. That's the teaching of, like, It doesn't, if you take OCaml, for instance, OCaml is inconsistent as a type theory because you have arbitrary recursion. So you can write a function of type for all alpha alpha. That's inconsistent. Nonetheless, in OCaml, true and false are not the same, right? So even though there are like programs that do not terminate, I'm very happy to compute with stuff that terminates. If it doesn't terminate, that's my fault. But it's not because type theory is inconsistent that it's useless. Since there is computation gives you information even though you can prove anything. There are various ways to prove things, so there is that. That brings us to the second point, which was the equational consistency. So that one is the important one from the point of view of the computer scientist. That's the one that says that true is not the same as false. And if I have an equationally inconsistent theory, then okay, here probably completely useless because now not only every type is inhabited, but everything is the same. So you can't do anything very interesting with that. So that property is the really one you care about, not the real one you care about, not the consistency. That might be interesting depending on the context. Equational consistency is really a critical property. What did I say after that? So
decidability of type checking.
Decidability of type checking. Okay. So that one has, I think, two motivations. There is a theoretical and a practical one. So let's start with the practical one because it's better explained. Basically, you want to implement your type theory in a proof assistant. Otherwise, what's the purpose? Like, oh, I wrote a lot of squiggles on a paper and great. And I proved like I worked a lot to prove things, and then it's completely useless because that's just like some scribble on paper. So you want things to be formalized on a computer to be run, because that's what we do. And having decidability of type checking is very important for that, because it tells you that you can actually faithfully capture your type theory in your proof assistant. Otherwise, you get in the situation of the lean proof assistant, where you've got these two-tiered system where you say, yes, there is implementation, like this is the kind of the real world thing, like it computes. Sometimes it says yes, okay. If it says no, well, you don't know. But if it says yes, you're sure. And then you've got like the platonic world of like epicycles floating around, like your planets are ordered in the perfect world where the Earth is at the center. And then you get all the funny things. And that's the ideal world. But, we mere mortals are living in the practical world. So in practice, you get two theories, and you can just say that one is an approximation of the other or something. But it's not really, there is some kind of, I do believe that there is some kind of bad faith in this kind of argument. And it's always better to not have an impedance between what is actually the idealized system, okay, this is defect. Like, this is not something. It might be the case due to historical accidents, but if it's the case, it's something that should be solved, not something that should be made worse. In particular, you want to have decidability of type checking, because that tells you that the system you implement is really the system, not some actual thing that is only an approximation of ideal world. The other reason is a foundational one, so that was a practical reason. The other reason is foundational because basically I'm very wary, let's say, of your meta theory. So there are many ways to phrase logical systems that may result in your meta theory flowing into your theory. So let me explain that. So typically, and maybe I'm going to answer a little bit what we were going to talk about after that. When you do realizability, like if you have a semantic definition of truth, so in realizability you say morally, like for all x a, if somehow for all x in the meta theory, which is like a for all in letters, a of something, whatever, like doesn't really matter. But you have to define the validity, you define provability in your theory in terms of truth, which just means provability in the meta theory. So this is kind of, depending on the exact nature of your theory, this can be very bad, because it means that people might not agree on what it means to be provable in the system, because they might disagree in the meta theory, right? Like for instance, if you take clean irreducibility, if you believe in classical logic in the meta theory, then you can prove that Markov principle is interpreted. If you believe in in anti-classical principles, you can disprove Markov principle. So this is very bad, because that means that somehow the system you defined is not foundational, because there is no objective notion of truth. So if you have a decidable type checking, it means that it rules out completely any kind of potential meta theory. There is a universal witness which is like you've got your type checker. That's a program. Okay, so let's be track A for a second. It's the number. It's a concrete thing. I can write it on the paper, like a few sheets of paper if you want. But there's a type checker, so I can write the type checker, and there is nothing else beyond that, right? The whole truth of your theory is checked by this type checker. So you could always argue that, but maybe it will not, because due to Gödelian tax, it will not terminate or something. But this is the only act of faith that you need there, and you know that this is a irredeemable act of faith, because like to prove the termination of your type checker, you need a stronger meta theory.
Oh, right. Yes.
But that's it. The worst thing that can happen is that your type checker loops. But you know that if you, regardless of the meta theory you believe in, like eventually it should reach a proof of whatever. So either it loops or it finds a proof. I'm using classical logic in the meta theory. I'm sorry, but so is life. So somehow there is the decidability of type checking gives you some kind of a guardian, like an oracle that is completely finitely described. And you don't need to believe in anything else. Like you run your program, you see what it tells you. End of the story.
This is what allows you to trust the QED.
Yes, somehow. It's really, it's not only trusting the QED, it's also saying something about the absoluteness of your statement. There is no way somebody can come to you saying, actually, I believe in something like my mental model of true mathematics is like, I don't know, I believe in non-consistence, like I believe that PA is not consistent or something, some weird like batshit crazy statements, okay? But in this situation, these people cannot really complain. Like the most they can tell you is that it's going to loop, but that's it. They cannot say, I know, actually, your one is going to say yes, the other is going to say no. That's not possible. It's either it says yes, it's valid, or it loops. No other possibility. So there is a objectivity. It gives an objective meaning to truth, which is not the case when the meta theory can actually pollute your interpretation of the logic.
Mm-hmm. I see.
So if the algorithm answers, everybody is bound to agree on the answer.
Yes. That honestly is why we are so keen about theorem provers, right? Because we can trust the QED, because this is absolute, exactly, the absoluteness of your statement.
Yes, it's
of your proof.
It's a concrete. Yeah, the proof is a concrete thing that you can check. That's the reason like many people are confused about the Gödel incompleteness theorem, because like there is often there are three conditions I think for a theory to be subject to the Gödel incompleteness theorem, and people often forget about the third one, which is like the type checking needs to be recursively enumerable.
Let's go through each one.
Yeah. So, are we opening parentheses?
Yes.
The three conditions are like if I'm not mistaken, you were saying that there are many ways to phrase it. Let me phrase it in a way that is constructive, hopefully. So, a system that is both consistent, okay, so it doesn't prove false. Complete, so either it proves no. Okay, damn, I'm already doing the.
Yeah, I already felt in this.
I'm already doing it in a very strong constructive way. Okay, let's put it that way and believe in classical logic. That's fine for a second. So consistent, complete, which means all formulae are either provable or their negation are provable. And the third criterion, which is very important, which is like the actual decidability of the derivation rules. The derivation rule are like you can actually check that a proof is a proof. Like you've got a recursively enumerable, I think is enough.
Oh, that's what it means. Okay.
Yes. So the third, you just realize
yeah, exactly. That's why we forget, because we don't know what it means.
Yeah. It just says I can check that a proof is a proof.
Exactly. Right.
Okay. Right, and if you satisfy these three things, okay, and then you need arithmetic. I forgot about that. But like,
yeah.
You need arithmetic. You need enough to encode like lists, basically.
Right.
So if you have these conditions, then you are inconsistent.
Either incomplete or if it's complete, then
you're,
it's inconsistent.
if you're actually not sound. Whatever, it's a contradiction.
Right. But then, so what are you saying that this? So you were talking something along the lines of like, okay, I have this ability of type checking, and what was the point that it should fall into the Gödel incompleteness
because a theory that is not actually the Gödel incompleteness theorem is a good litmus test for your theory to be a foundation. If you're not prone to Gödel incompleteness theorem, then you're not a foundation. Okay, maybe this is not a formal statement somehow. This is more so why? Because you want your foundation to be consistent, important, otherwise whatever. You want your theory, you want your theory to contain arithmetic, and you want your theory to be computable. Like you want to check the proofs, because otherwise, because like there are very good definitions of there are things that satisfy all these properties except for the computable part. There is a very famous one which is called like a true arithmetic. So true arithmetic is defined as my system. All the statements provable in my systems are statements that are true in the meta. I mean, provable in the meta theory. That's the definition of true. And this is completely useless because like there is no way. Like, okay, is it true? Is it false? I don't know. Like there is no proof. Like
right.
Just pluck a truth out of the Santa Claus meta theory. Say, I proved something. There it goes, and you have no way to check that it's a correct proof.
So how I hear this in a very naive way, like trying to translate the most naive way possible, is that so what we're trying to achieve here is, okay, so originally what is Gödel incompleteness theorem is solving the second Hilbert's problem, or third, whatever. And the problem there is like, okay, I need a good foundation of arithmetic, and I want to know if it's complete and consistent, right? And so in order to solve that problem, okay, so what are the rules of the game we're playing, right? So that's the main theorem. Okay, give me the rules of the game to begin with, and show me that I can play the game following these rules, right? This is the decidability of the type checking. So if you cannot even play the game and like if you cannot even follow these rules in an obvious way,
because nobody can agree on the on the rules, like, whatever.
It doesn't even make sense. Like we're not even like asking a proper question about what we're trying to achieve here. That's a very good way to put it. Should we go to the next one, or we have more about the decidability of type checking?
Yeah, let me put more in my brain the fact that I should recall you about the Gödel incompleteness theorem and double negation translation and dialectic after that.
Yes.
So what was the next one you said?
Canonicity. Computational interpretation.
Okay, so that one is important for the computer scientists and the mathematicians to some extent. So in most foundations of mathematics, there is no canonicity. And the reason is that, for instance, let's summon again Gödel incompleteness theorem. I think that's going to be a staple of this interview. So in ZFC or in any classical system for that matter, that has enough choice, you can prove that there exists a Boolean, so a number that is either 0 or 1, such that, okay, so you pick a formula first, say phi, for any formula phi in the system. So you can prove that there exists a formula, Boolean B, such that if B phi, and otherwise, if not B, then not phi, right? Okay, so somehow you can reflect provability through a Boolean, right? Now pick your favorite indecidable statement from your system, okay? Phi, you instantiate phi by this indecidable statement, and suddenly you know that there exists a Boolean, okay, so that decides an indecidable statement, okay? Moral of the story, this is not a Boolean. This Boolean is neither true nor false. It's some kind of a eldritch Boolean that is like radioactive of any part, like very hairy and it's
Schrödinger Boolean.
Yeah, it's either true or false, but you don't know which one.
Right.
And you know it's worse than that, and you know it's neither from the meta-theoretical point of view. You know that it cannot be true because otherwise phi would be provable, and it cannot be false because otherwise not phi would be provable.
Right.
What the fuck? You know? So this is why we care about canonicity, because like we want that when you say that there exists a Boolean, then there really is a Boolean. And I'm not trying to trick you into believing this kind of weird unicorn-like Booleans. So canonicity is really saying that. It says if I take, so normally you state it with natural numbers. It says if I give you a closed natural number, then actually this, so let's call it n. Actually n is equal to an actual concrete natural number, equal as in convertible. That's mathematical way to phrase it, because that's not very interesting. Like you could have a theory that is defined, and once again in the meta theory saying, equal, a conversion is actually equality in the meta theory. And then, yes, with that, like you can say also that with the Boolean example I gave, if you take true arithmetic, then there exists such a Boolean. It's either true or false, but you don't know which because you use classical logic in the meta theory. But the second stage of the statement of canonicity is the one computer scientists care about. So not only you know that if I give you a Boolean or a natural number, it's really a Boolean or a natural number from within the conversion of the theory, but you actually have a computational way to extract this Boolean. So if I give you a closed term of MLTT that has type nat, then there is an algorithm that will give me a natural number that satisfies all the properties satisfied by n. And this is just like normalization. You take your term, you normalize it, boom, it should give you a natural number. And that's the computer scientist canonicity. And this is very important for programming, because that means that you can actually evaluate your programs and you do not get weird results. Because like in actual programming languages, it's harder than that. Like you have like, there is a little bit, as soon as you have like side effects, things get a bit blurry. This is why in PLT you have to be careful about the progress and preservation statement. Because typically you care about values. So you say a value is like a value of type bool must be a Boolean, but a computation of type bool can be weird. Like if you have side effects, for instance, you could like raise an exception. Like there are terms of type nat that raise exceptions, camel or something, and these are not natural numbers. If you have like mutable state, you can do weird things by interchanging things or whatever. If you have non-termination, you can just loop, So canonicity is a property that is very nice for type theory that you care about when you compute, but that can be weakened as long as you are clear about the kind of contract you are making with your user. Like you want to know what the normal forms of your terms are. Yep.
And okay, so how do you term progress and preservation terms of canonicity?
So I think one is completely trivial because there is no reduction. So how would I go? So what do you want to get exactly?
I don't know. It's because like you said, I originally asked like if you care about progress and preservation, and you said that it's
very related.
It's a side canonicity.
So normally for progress, I would say you can just state progress the same in Martin-Löf Type Theory. You say that a term is either a constructor, like a weak normal form, or it reduces. That's there is no other. It cannot get stuck. So that's also true in Martin-Löf Type Theory. Preservation is subject reduction, so that one is also true in Martin-Löf Type Theory. So there is maybe what do you call because what do you put the condition where you analyze maybe in progress? In progress, you also say that if you reach a value, it must have a specific shape, right? You state that depending, you have to be careful about how you phrase things, I guess. But okay, a bit of so some part of progress is just we get reduction somehow. And canonicity is that is the other fragment saying that the values are actually of the expected shape. And preservation is subject reduction, which is also a very important property. So it's not that it's critical, because like if you take a very mathematical stance, like actually reduction is not even a concept in the algebraic presentation of type theory. Right. So you could just get rid of a subject reduction and say, because there is no reduction a priori, you can strap it atop the type theory after the fact. But a priori, you don't have to care about subject reduction. But I would argue that most interesting models of type theory are somehow realizability / logical relation based on reductions. And in this case, it becomes very hazy if you don't have subject reduction, because you have to always be extremely defensive about whether you can reduce and still be well typed, because it might not be the case anymore. So for metaphorical properties, like if you don't have subject reduction, you are bound to have weird models. So it makes the meta theory of the type theory much more contrived to work with. It's not something. I would like to say something in like small parenthesis about the emergent complexity of type theory. So there's something that is very hard to convey in like verbally, which is the amounts of way type theory can go wrong when you try to do its meta theory, right? There are a lot of properties that are very easy when you do like simply typed or system F or F omega. Even F omega is simple in that respect. So there are a lot of properties that are easily proved by induction in simpler systems, but that are basically, I mean, not equivalent, but not far from being equivalent to consistency of your type theory when you have like dependent type theory. So like subtle properties, like if the word like injectivity of pi types rings a bell, that's one of those. Like these are kind of properties that are very easily proved in simpler systems, because you have a very limited amount of computation in types that can go completely wrong. When you look really into the models of type theory, there is some kind of emergence, and I'm not sure how much of that complexity is accidental and how much is really intrinsic. These models are complex, and there are many ways in which they can go wrong. And if you start removing parts of things you would expect, like good properties like subject reduction, then it will complexify. It will make your life as a meta-theoretician of the type theory harder. As a general rule, the more properties my theory enjoys, the better I will be off as both an implementer and somebody who is actually proving that the theory makes sense.
So you're saying that having these nice properties will actually make your life easier implementing.
Yeah, down the road, you can always say, nah, I don't care about it, but you will have to pay for it at some point. So if you can have them, please, because otherwise you'll suffer.
Well, so another point that you made that we didn't come back at is that Turing completeness is related to the decidability of type checking.
Yes. So I'm not sure I can phrase that formally, but if your type checking is given by means of computation, the root of the problem is like Turing completeness is not totality of a function is not recursively enumerable, right? Like maybe you don't care about whole just function, just term. So in that case, what you care about, it's covariant in one hand and contravariant in the other, right? They can always, if I give you a program, you can always check that it terminates. Maybe it will loop, but if you found a proof, you know that you reached a stop. But if you put that on the left-hand side of an arrow, then you're screwed because now the arrow is contravariant. So you lose both recursive enumerability and co-recursive enumerability. So you're in this kind of morass of arithmetic hierarchy where you go one level up or whatever. It doesn't really matter. But the point is, if you're Turing complete, there is no way to capture totality in a finitesic way. So you won't be able to write a program that checks that. You can't normalize things a priori. So you won't be able to apply the normal techniques for type checking in general. So it needs to be given in more precise settings. Like I'm sure I can find a counterexample where you have both Turing completeness and decidability of type checking, but then you have a crappy type system, right? So like you could say that unit type lambda calculus is decidable as type checking and is Turing complete. But if you frame correctly the precise hypothesis I'm caring about, so dependent types. What do I need to do that well? I think I need a little bit at least a very tiny bit of dependent type. But as soon as you have potentially non-terminating functions that are flowing in your types, and you need to compute on these functions, you are toast. Because like you only able to compare the output of two functions, and that might loop. So you at most you might be able to be recursively enumerable, but not anything else.
Can you quickly summarize what is recursively enumerable here?
Just that you can write a loop, and if it says yes, then you're fine. Otherwise, it might loop. Like if you're asking a Boolean question, so you know that a Boolean problem. So the root of the problem is like actually Booleans in non-terminating programming languages are three. There is true, there is false, and there is bottom. And so recursive is the best case. Like it always answers true or false, right? Okay. No bottom. So recursively enumerable means that if it has to answer true, it will answer true eventually, but you don't know anything about the false case. Like you lose completeness on the negative case. And really for co-recursively, like if it answers false, it will answer false, but otherwise it will loop.
I think when I was taking that Turing machine classes, we called it something else. Is it decidable? No.
Yeah, so it's related. So
right. I think we called it something else. That's why I was a little confused.
Yeah, no, it depends on your precise nomenclature, but it's basically the same.
Okay. So is there anything else for us to cover in terms of good theorems that we care about, of good properties of our language?
I don't remember. I made a remark, but I don't remember what was the remark about the last one.
Yes, I'm coming. I know the remark that you made, but I feel like I'm literally, what's the word? When you have, I feel that I'm torturing you for more than 1 hour because it's been this time that we still haven't said the word dialectica.
But we haven't talked about realizability. I think like maybe it's required before dialectica. But
no. We have touched realizability many times, and I think it's finally the time to take that out of the head.
Okay.
If you have paid close attention, you will notice that this episode is kind of a continuation of a topic I was having with Mario in the previous episode when we were having a conversation about why it's okay for lean to break a few properties in type theory that people care about. And Pierre-Marie is known to be pretty critical about that since he believes that if you do not hold these certain properties, then your type theory will pretty much eventually crumble on its own weight and will make the life of the developers much harder. So I wanted to have him over and really dive into this question of why he thinks that. And well, it turns out that the thing is that Pierre-Marie is an extremely sarcastic guy and and it's extremely funny to talk with him. He's so smart, and we really avoided to mention lean in this episode because we didn't know how people would get the message behind. So we really focus on the reality here that we're talking about in the sense of the type theory itself. Like, what are these properties? Why do we care about them? And that kind of thing. So I just wanted to give you guys a little bit more of context of what we had in mind in this episode. And the conversation actually continues. You'll probably notice that I stopped the recording in the middle of the episode. And the reason for that is that now the next segment will be completely unrelated to all of this. We're going to actually talk about the things that Pierre-Marie is interested about and his PhD topics and some of his stories. So looking forward for the next episode. See you guys pretty soon.
Este podcast foi editado por Play Áudios.